So when you need to figure out whether a reaction is likely to occur via an SN1 reaction or an SN2 reaction, there are 4 things that you want to consider. The first is the substrate. So both sterics and the stability of the carbocation will play a role here. The quality of the leaving group is important. The strength of the nucleophile. And also the solvent. And we'll take a look at each of those things. First, the substrate. You have methyl, primary, secondary, tertiary, allyl, benzyl. So a methyl reaction with a leaving group, this will go SN2. Primaries can go SN2. Secondaries can go SN2 slowly. An allyl can go SN2 because there's not very much sterics at this carbon here. And a benzyl can also go SN2. For SN2 substrates, less sterically hindered is better. For SN1, we're going to look at substrates where the carbocation can be stabilized, which usually is more sterically hindered. So for SN1 substrates, sterics or resonance stabilized is better. So benzyl will go SN1, allyl will go SN1, tertiary goes SN1, secondary can also go SN1. A vinyl and an aryl, where the leaving group is directly on the double bond, these will not go SN1 or SN2. Those are both sterically hindered and cannot be resonance stabilized. So when we're looking at the nucleophile, we mentioned a while ago that SN2 must have a strong nucleophile, so it must be negatively charged. In the SN1, it's forming a carbocation, so it just needs a nucleophile, so it can be a weak one. The rate of an SN1 reaction is not affected by the nucleophile, it only depends on the substrate, whereas the rate of an SN2 reaction is affected by nucleophile as well as the substrate. So a strong nucleophile present in large concentration favors SN2. For the leaving group, SN1 must have a great leaving group. If it can't leave on its own, it's not going to go anywhere. It's not ready to leave. Then it won't leave and it won't form a carbocation. The leaving group is determined by how well the atom or group can stabilize the negative charge. If it's better at stabilizing the charge, it's going to be a better leaving group. So the best leaving groups are the halogens, not including fluoride, the tosyl groups, and then water, and your worst ones are here. If there's a bad leaving group, the carbocation is not going to form. And in an SN2 reaction, you just need a leaving group because the nucleophile is the one driving the reaction. In SN1 reactions, for the solvent, it needs to be polar protic to support the anion and the cation. So here's the cation, the anion being supported by water, which has the hydrogen to donate. The SN2 needs to be polar aprotic to support the cation only, which makes this more nucleophilic. So determine what method each reaction is undergoing. So this is SN1 or SN2. And determine the product. Include stereochemistry where relevant. If we're looking at this reaction here, I'm going to look at my substrate first. This one is secondary. There's a chlorine with the 2 carbons on either side, which means that it could go SN1 or SN2. Okay, then I'm going to look at my leaving group. That's chlorine, which is a pretty good leaving group. We have SN1 or SN2. The next I look at the nucleophile. This is NaOH, which is a very good nucleophile. Again, that's SN1 or SN2, because SN1 just needs a nucleophile. And now I'm looking at the solvent. This is water, which is polar protic, so that points to SN1. So my reaction is going to go SN1. So I have my leaving group. So leaving group will leave. Actually, the substrate here is benzylic. This is loss of leaving group. So I have an OH minus. This is my nucleophile. This is the electrophile. I'm going to do a nucleophilic hug. And the OH gets added there. The stereochemistry here, this would be the product with the OH substituting. So the stereochemistry, when you have those squiggles, that means mixture of stereochemistry. So with an SN1, you get 50% retention and a 50% inversion. All right, in this one, we go through the same process. So look at substrate. That one is secondary, so SN1 or SN2. Leaving group, bromine, that's SN1 or SN2. Nucleophile is great. Could be SN1 or SN2. Solvent is acronymy, which is polar aprotic. This is SN2. So I have nucleophile, electrophile, leaving group. So my nucleophile is going to hug the electrophile at the same time as the leaving group leaves. And it's also doing an attack from the back side. So it's going to attack from, I guess, the front side here. And that will become wedged Cn plus Br minus. And that was a nucleophilic hug. And then loss of leaving group. And then the stereochemistry got switched from dash to wedged. All right, in this last one, again, determine the method, determine the product, include stereochemistry where relevant. For my substrate, is primary, which would indicate SN2, but none of the other directions point in that way, so this would be no reaction. So I have a substrate with a primary, which is SN2, but the solvent does not support SN2, the nucleophile does not support SN2, and the leaving group does not really support SN2 either, so this is no reaction.